So good morning, good afternoon, good evening. Thank all you that are joining us today for our next IEEE CASS Rio Grande do Sul Talk 2021. So you have here in this flyer in the bottom all the societies and the institution that are organizing this series of events and talks. So today we have the pleasure here to have Professor Eduardo da Silva from Federal University of Rio de Janeiro, Brazil. And today the session chair will be Professor Bruno Zatti from Federal University of Pelotas. But today we are here to attend this talk by Professor Eduardo da Silva. And so now I give the floor to Bruno Zatti. And thank you again, Eduardo, to accept our invitation. Also, thank you, Bruno Zatti, to accept to be the session chair today.
Thank you, Professor Hayes. It's actually a pleasure for me to chair this session with Professor Eduardo da Silva. He's going to speak to us. His talk is entitled New Modalities for Acquisition, Representation, Processing, and Visualization of Image, Plenoptic Functions, and Light Fields. Professor Eduardo has his title on Electronics Engineering from the Instituto Militar de Engenharia in Rio. His master's is from the Federal University of Rio de Janeiro, and his PhD in electronics is from the University of Essex in England from 1995. Professor Eduardo is currently professor at the Federal University of Rio de Janeiro since 1989. He is co-author of 4 books, including Digital Signal Processing, System Analysis and Design, published by Cambridge University Press, and with editions in English, Chinese, and Portuguese. His research interests are on signal and image processing, signal compression, 3D videos, computer vision, light fields, and machine learning, together with applications to telecommunications. Also, he works with oil and gas industry. He's currently the requirements vice chair of the JPEG group at ISO, and is also editor of the standard JPEG Plenoptic image coding system. Of course, Professor Eduardo has published multiple articles and also has a long-standing contribution to this field. So Professor Eduardo, it's actually a big pleasure for me to host you today. Before giving you the floor, I just would like to tell our attendees that they can make their questions by writing in the YouTube chat, so I can read and bring the questions at the very end of Professor Eduardo's talk. It will be a pleasure to bring the questions. I can see that we have guests from Brazil and also from abroad. So, Professor Eduardo, the floor is yours, and thank you for accepting our invitation today.
Okay, thank you very much, Bruno, for your words, and I would like to thank Professor Reis and the Rio Grande do Sul IEEE CASS chapter for inviting me for this interesting series of talks that it has been promoting. Very useful and very interesting. Okay, and so we talk today about new modalities for acquisition, representation, processing, and visualization of images, Panoptic functions, and light fields. With this talk, I would like to give you an introduction about light fields. I would just like to say that this presentation has been elaborated along the years in collaboration with Professor Fernando Pereira from Instituto Superior Técnico and Instituto de Telecomunicações from Lisbon, Portugal. Okay, so when we look at images are present in all aspects of our life. Okay, images are very important, and actually visual information is very important for human beings, and a significant portion of the activity in our brains is devoted to the processing of visual imagery. And because of that, visual experiences are very important, and the video traffic today is huge and increasing. Okay, and actually, and because of this prevalence of visual experiences, we need crescent types of visual experiences. The more immersive, the better. And so we have up to some years, and into a great extent now, we live with what we call the frame-based model. It's like a 2D window for the world, a two-dimensional window. Okay, and we have, okay, in the past 15 years, we have been evolving from standard definition television, high definition, 720, full HD, 4K. We are now already talking about 8K, trying to improve the experience. We also go to HDR images and so on. But we have the fact that the world is three-dimensional. It's not two-dimensional. But for a long time, and this dates back to the end of the 19th century, we have ways of trying to represent 3D information using stereoscopy. Like we present one image to the left eye, one image to the right eye, and the brain integrates these images. And so we have, since the end of 19th century, devices like these, okay? And more recently, we also have, from the last 10 years or so, a bit more, like 3D cameras using two cameras, using the same principle. And actually, if you go to history, we can see that since 1838, when the first stereoscopy experiments and gadgets began to appear, and actually in the Victorian era, they started to the stereoscopic images began to become popular, and 3D movies started like at the middle of 20th century, and they got a boost when the movies like Avatar and so on, they appeared. Okay, but 3D video, as you can see, is mostly stereoscopic video. And what does it mean? And what does it mean for our experience? Because people say, okay, no one wants more 3D TVs. No one buys 3D TV sets more. And people say, okay, isn't 3D dead already? Why are we caring about 3D? Okay, because due to many facts, because the world is not two-dimensional, it's three-dimensional. And we can have 3D with more than stereo parallax, and 3D application go much beyond what in broadcasting and entertainment and so on and so forth. Okay, but the problem with 3D, the critical factors for the success of 3D is, okay, we have to overcome certain hurdles. What is it? Like especially visual fatigue, which is quite annoying. The need for when you go to the movies, you have to wear glasses, and we don't have too much 3D content available yet. Okay. Yeah. But before going further into that, let's talk about some basic 3D perception concepts. Okay, we have our eyes. I will not talk about the eyes, but the eyes are our sensors. And how does the stereoscopic 3D perception happens? It means I have one image made from the left eye, another to the right eye, and the brain integrates those two into a 3D image. As we say, we have looking at the object from two different viewpoints, we can create the 3D perception. Okay, and there is some mathematics behind it. Even if you have two cameras conveniently calibrated, you can synthesize the 3D scene if you have the point correspondences and so on and so forth. But 3D is not only stereoscopy. Like say, we have other cues. For example, we have monocular cues for 3D perception or perception of depth. For example, we have linear perspective. What's that? We can see like this. If you have, if you see lines converging to a horizon line or vanishing points, we guess that we are seeing a 3D scene. We have occlusion, because if you have one object in front of the other, it means that the object that is occluded is probably behind the other one. We have also shading, because the shading also gives us a sort of 3D impression, as we have here. And we have texture also can give us an idea of 3D, and we have also prior knowledge. For example, if you see a big person next in our depth in our field of view, besides a very small person, we guess that the second person is not very small, but is farther behind. We use our previous knowledge also to infer 3D. Is this using only one eye? And we have other cues like for 3D perception. That one is stereo parallax, which is what we have in our 3D movies and 3D TV. We have we show one image to the left eye, another image to the right eye. We can do that by either having a glass that is synchronized with the display, the glasses shut the right eye and show the image of the left eye, or shut the left eye and show the image of the right eye, and do some multiplexing. We can do this using polarized lights, as we have in the movies, so that we show different images to the left eye and right eyes, and we have this impression that we're seeing a 3D image in front of us. But we have another important cue, that is motion parallax. What's the motion parallax? Okay, if I look at the scene and I move, for example, the objects that are closer to me, they move faster than the objects that are further away from me. Okay, this is motion parallax, which is very important for us, because imagine if I just close one eye, I can still have a 3D impression, mainly because of motion parallax, because when I move, the perspective changes, and I know that I'm looking at a 3D scene. Okay, and there is also another cue, which is vergence, that some muscular rotation. It means when I'm focusing some object in front of me, my two eyes somehow they converge to the object. Okay, these are other cues. And see, it's just we see somehow like an object that is seen by the left eye and right eye in two different positions here, or this object also left eye and right eye, two different positions, and from these positions I can compute the 3D geometry. Okay, but let's see reasons why the 3D experience, as it mostly is today, is insufficient. there are some problems. Let's see what we call the accommodation versions conflicts. Suppose we are at home and we have our 3D TV sets, and it shows me, or using polarized light, glasses, or any other means, they show a different image to the left and right eyes. And we see a 3D image forming in front of me. And it is in front of the screen. Okay. At the moment that my brain perceives that there is an object in front of me, what do I try to do? I try to focus the object that is in front of me. But actually, the images are not in front of me. They are at the screen. Since they are at the screen, what happens when I focus on the object in front of me, I lose focus because focus is behind. Then when I release focus and try to look at the screen, the object is in focus, but I'm not looking at the object, but I'm looking behind the object. And this creates some sort of conflict. And this conflict, they may make you sick, may give you headaches, and so on, because it creates some tension in my visual system, brain and visual muscles, and so on. And this is a big problem. Another problem is given by the motion parallax, because when I see a 3D object in front of me, when I move, I expect to see different perspectives of the object. But a 3D, an image generated by 3D stereoscopy, when I look at the image, I will see a 3D image, but if I move, the image shown to my left eye doesn't change. The image shown to my right eye doesn't change, so I don't see parallax. And so, again, my visual system, the brain and muscles and so on, gets confused. Because when I move, the object was supposed to show different perspectives. It doesn't show, and there is also tension on the muscles from my visual system. And again, it may give me a headache, it may give me nausea, fatigue, and so on. And so this is a problem that we have. But and it's interesting because I guess this was one of the main reasons why the 3D TV, they were not very successful. After some initial fever, everyone wanted to buy one and so on, but then this fever receded. Why? Because when I'm in front of the TV, those two problems, they happen. Because the TV is close to me, so the vergence accommodation conflict, by me focusing on the image and the image getting out of focus, and also the motion parallax, because if I am at home, I am at my couch, for example, I will likely move, and when I move, I would expect to see the parallax change. When I'm in the movies, for example, things are a bit different. Why? Because, okay, I'm seeing a 3D movie with my glasses, but the screen is far away from me. And the objects, although I see 3D, they are not very close to me. So I do not expect, if I move a little bit on my chair, I do not expect to see motion parallax, because I'm at the movies, I will not move that much. And I don't expect to see motion parallax. And the focus on the screen is far away from me. So I have infinity focus. So I don't have the accommodation vergence conflict. And this is one of the reasons why the 3D movies are still somewhat still alive, while the 3D TVs, they do not sell anymore. Okay, then one possible solution for the discomfort, this 3D comfort, solving the motion parallax problem, is having multiple views of a scene that It means I record the scene using multiple cameras here, like here, and using these multiple cameras. And when I move, I have some tracking system that tracks the way I move and changes the image it shows me. So the motion parallax can be simulated. So this is one possible solution. Okay, the problem with the solution is that we need a lot of images, and we need synchronized cameras, both in terms of spatial position, orientation, and timing. So it's not a cheap solution to do so, but it's one possible solution. Another solution for this more immersive thing is like the 360 video, where we project a video on a sphere around me, and when I move my eye, when I move my head, I see different parts of the scene. Okay, and attached with that, we have what we call the visual degrees of freedom. It means in 360 videos, very easy to have like three degrees of freedom. It means I will move my head like this, pitch, I will roll my head, or I will make a yawn on my head. And in these cases, I'm rotating my head. I can have this sort of spatial experience. But we have another one would be like 6 degrees of freedom. It means I can also, besides rotating my head in several ways, I can also move back and forth, move sideways, go up and down. It gives more info, and this is more difficult because when I start moving like this, I need to have parallax. Okay. And let's see, ideally, what would we need? Because as I say having parallax, we would need a lot of different images from different perspectives, and I will have to switch them. For dealing with accommodation versions, I would like to see the image as it was actually in front of me, emanating rays from those positions. And so, as this guy said, this Gabriel Lippmann said, okay, the most perfect photograph currently shows only one aspect of reality. It reduces to a unique image fixed on a plane, as a drawing or a painting would be traced by hand. Can we ask photography to render all the richness the direct view of an object offers? Okay, then we go from this desire, we go to the plenoptic function. What is a plenoptic function? Okay, this is like with this Pumple's name. Let's see, what is it? Actually, it's a description of all visual information present in the universe. This would be the plenoptic function, a sort of very ambitious function. But actually, it is effectively given what is all the visual information. If I can describe the electromagnetic field around me in the visible spectrum, I would be able to represent everything I'm seeing. But you can say, oh, but this is very complex. But we can simplify it by some assumptions. What are they? First one, we are talking about non-coherent light. It means light has a frequency, the electromagnetic energy, but it has no phase. I'm not talking about laser, interference patterns, anything. We put light here, and if light adds like noise. So if light adds like noise, we can represent light not by frequency and phase, but only using an energy distribution through frequency or energy distribution to wavelength, like a power spectral density function that we call P of lambda. where lambda is the wavelength of the electromagnetic energy, because we are not caring about phase. First simplification. Another one, the electromagnetic wave at one point in space, x, y, z, can be seen as a superposition of many electromagnetic wave fronts coming from different directions. Okay, and for each direction, I have a different electromagnetic wave front. So, like in the wave front that is propagating like this, I represent by a ray of light. Okay, so we have in one point in space, x, y, z, we have rays of light in different directions that we can represent by theta and phi, the orientation and azimuth. So this power spectral density now doesn't depend only on the wavelength, but also on the point in space that I'm measuring and the direction I'm measuring, because it's a point in space and a given ray of light at this point in space. And also, of course, the energy varies with time. So we would have this function, what is x, y, z point in space, theta and phi orientation and azimuth, wavelength, and t. It's a function of 7 variables that can represent all the visual information that is reaching me. And this 7-dimensional function is referred to as the Plenoptic function. And that would be ideally what I would like to represent in order to give the fullest 3D experience. And just a representation here, we have a point in space, a light ray in a given direction, and it will give the Panoptic function here, represent, depending on the point in space, the wavelength, and the orientation and time. Okay? And now let's see some important simplifications. Number one, in practice, we do not need to know the electromagnetic energy at all wavelengths. Why? Because our eyes as humans, we have only 3 types of sensors, like the red, green, and blue, and our brain, it combines the red, green, and blue information as measured by those different sensors and generates an impression of color. And so instead of having the Panoptic function depending on x, y, z, theta, and phi, lambda and t, instead of lambda, we need only 3 components that do not depend on lambda. And this is usually enough for us human beings for representing color information. Okay, then the first simplification, we have dropped one dimension by putting 3 color components. Okay, then the first simplification is what we call 2D video. What's a 2D video? Actually, my point in space is represented by my camera, the aperture, the aperture of my camera, by which the light rays go through, and it reaches the camera sensor that has coordinates UV. So actually the position of the camera, I don't care about it. I am assuming that the camera is fixed. So the Panoptic function now depends only on the camera coordinates that the ray reaches and the time. So is depending on UV and T. This would be our video. And this C is a color component that can be RG or B. Okay, then it's first simplification to the video, but today. We have also the multiview video. What is a multiview video? Actually, the multiview video we have now by the camera centers that we have here. They are in several positions. We have several cameras, each one in a given position. And so by putting the indexes K and L of the position of my planar array of cameras, we could have like a set of videos that depend on KL, the position of the camera, UV and T, which is the video recorded by this camera. So it would be we would have 5 dimensions of our Plenoptic function. One example, we will have a scene like that. This is a scene for each camera using its K and L position and a position U and V inside it, varying in time. It's our multi-view video. We have another one which gives a further information. Okay, my array is planar. Okay, we can have we only know position X of the camera in K and L, but we also have the depth information. If we have the depth information, we could infer the 3D position of the point at the scene. So we could have a Plenoptic function, KL, D, UV, and T, where my depth depends on KL, UV, and T. Okay, and we have this multi-view video plus depth. We have also the point clouds. The point cloud, they're a bit different. It means that for every position in space, X, Y, Z, they assign a color, for example. So every point in space would have a color or a certain property like reflectance or color and incident light, reflectance, and so on. But if you go to a simple one, in which every point X, Y, Z has a color, it can be R, G, and B. So it would be, again, a 4-dimensional function of the 3D point X, Y, and Z and time. These are point clouds, which are also today widely used. Okay, the Panoptic function simplification that we will talk about today is what we call light fields. What's light fields? Light fields, my aim with the light fields, we can understand them as, okay, we are representing the Panoptic function inside a camera. It means I will represent all the light rays, but inside the camera. And how can we represent my light rays? I have the sensor plane of the camera, and I have the camera lens plane. So my light ray, it pierces the camera lens in the point UV and the sensor planes in the point XY. And we have in my function, we would have the intensity of the light ray would be dependent XY, UV, and T. This would be a light field. Okay, and we are also assuming that since we usually assume that there is not enough attenuation inside my camera. It means from the camera lens to the sensor plane to have any attenuation. So the intensity of the light ray is constant through inside my camera for a given light ray. So in this is a light field, which is a function with 4 spatial dimensions and 1 temporal dimension if it varies in time. Okay, and the light field looks like this, where we have this, each one of these, like these dots here, it would mean a given point, image of a given point taken in different directions. And we'll see more about that. And such cameras we refer to as Plenoptic cameras that record exactly this 4D field inside the camera. We have as examples the Lightroom camera, which was popular some time ago. Now Google bought the company that was producing them, and they are not producing anymore. But they have the Raytrix camera. That this Raytrix company is still very active and launches new models every year and so on. And it's also a light field camera that we have, for example, microscopy light field cameras, regular light field cameras. We have this ray shaper multiview camera that is an array of camera. We have this Toshiba light field camera model, which is also a very small module with a light field camera inside. We have this Pelican array camera, which we can see here, this 4x4 array of tiny cameras, the size of a coin. And let's see some images for us to have a gist of what our light field is like. It means in light fields, since I record all the rays of a scene that are inside the camera, I can combine those rays as I like. If I can do so, I can, for example, put the focus wherever I want, because I can combine the rays that I like to combine. Then this is an image from the Lightroom camera. I can, by clicking in a place, put the focus, and put the focus here. We'll put the focus here, I believe. Let's see a better image here. This image, for example. Oh, okay, I want to combine my rays and put the focus here. Then I have this image focus here. I can put my focus here. I can put my focus here at the back. This image is interesting. I got put here the image. My focus is on the tree. My focus is on the tip of the squirrel nose. My focus is at the body of the squirrel. It means using light field cameras, I can do interesting things because I can combine the light rays as I like. Okay, and how it is done. Okay, how it is done. This is nice image, gives an example here. Like I have a point here, and I put in front of my sensor plane, I put an array of lenses, very small lenses, what we call micro lenses. And so a given 3D point is focused by the objective lens on a given lens. But now, since the focus is here, each light ray will be recorded at a different point in on my sensor plane. So I can actually record for each lens the different rays that comes to this lens from the different directions in different positions. And so this way I can record, like I can sample the light and record the light rays emitted by an object. Okay, by looking like this conventional camera. I have this scene here. We have my main lens, image sensor. That's a conventional camera where I use the main lens to focus the image on the image sensor. And in the light field camera, we have a micro lens array in front of the camera. Okay, and it works as it was also illustrated by that image, which means I have the point in the scene, the different rays coming here, and the lens focus on the micro lens, and from the micro lens I can record the different rays in different pixels. Of course, I need to have a resolution of my sensor very high because I need to have as many micro lens as points as my resolution of the image. And behind the micro lens, I must have a much higher resolution to record the different rays that comes out of the object. And it's what we are seeing here, because for each micro lens, I see the different light rays that come to that micro lens. So actually what we do is that we using this, we capture the directional information. Let's represent this to simplify. Let's say we have a light field that for each light ray I represent with the coordinates UNV, that it pierces the camera lens, and the XY coordinates that it pierces the sensor. And we can represent this as a point in the, now I'm just looking at the horizontal position, like the X position at the sensor and the U position at the lens. And we can represent a ray by one point here. So, and since we have one 3D point here, it emits many rays that cross the lenses in many U positions. And if the lens is in focus, for every point here, all the rays here converge at the same X position, because all the rays that are incident here, they converge here. So the image is in focus. So each row here is a different point here that I am recording. Okay, and how do I record it? Actually, I have a micro lens array here that, using this arrangement of pixels behind the micro lens, I can represent this space here, XU. So, and that's actually how a Lightroom camera image looks like. I have two images here. This is the big image. If I look at closely, what is recorded are things like this. Here is the two noses, the nose of the guy behind the nose of the girl. And these are all the directional information of the rays for each micro lens. And using the directional information, I can have many viewpoints, like what we have here, for example, in this image recorded with a Lightroom camera. Okay, we can have many viewpoints, and we could do refocusing as we had shown before, but just have a quick idea, how do we do it? And so if the image is in focus, it means if I'm summing all the rays that converge to a given point, is to take this vertical line and summing all the rays along here. It means all the U direction rays, all the rays that cross the lens in different positions, I sum at a single point. But suppose that my image is out of focus, like say the image would form here behind my position. What would happen? For each ray, when you move it, I do not converge in a single X because my focus is further away. So as U moves, X moves. It means my rays that I am summing, they are inclined here in this direction. Okay. And so if I want to focus on this position, I have to sum the rays along this inclination. If I move my position closer here, further away, my angle will change. I will sum along a different direction. Here, instead, if my image is formed before what it should, so when I move U, the X position moves in the opposite direction, so my inclination is here. If I sum all the information on my light field camera in this direction, I will put the focus at another position, okay? And so like that, we can do this refocusing. So we can have an example, 3 different positions. The green is totally in focus on the micro lens array. The red the focus is before it, and the blue, the focus is after it. So we see the red light is the rays are along this line, and if we want to put the focus here, we have to sum all the red lines. If I want to put the focus here, I focus all the green lines. If I want to put the focus here, I sum all the blue ones. And so like this, we can do our refocusing. And examples, I have given you better examples. The Lightroom camera. And we have also some mathematics here that I will just skip it because this is a short talk, but there is a mathematics here, and we can do refocusing. We have formulas for changing the focal length if we have our light field, and so on and so forth. There is a mathematics about it. But I would like to call your attention to some more mathematics that are interesting. It means, let's see that we have a light field. Let's see, we have a camera here. This is the center of the camera. This is the sensor of the camera. The light ray goes through the camera center, and it intercepts the sensor here at the position U. The center of the camera is at position X, and my point is at position, here we just represent X and Z because we are just looking at the 2 dimensions. Okay, what will happen is when I change the S position, the U position changes depending on the depth of the 3D point, the distance of the 3D point from my sensor. And from the center of my camera, and actually for a given depth, I have my points along a straight line in the SU plane with a given inclination here. Okay, so as the depth varies, this inclination varies. Okay, and I can solve all the points that have the same depth. They are represented by straight lines in the SU plane. If I compute my Fourier transform in this plane, Fourier transform of straight lines, they are straight lines going through the origin, and the orientation is orthogonal to the orientation in space. If I have straight lines at different depths, they will have different inclinations, and we have different inclinations of straight lines going through the center of the frequency SU plane. Okay, what is interesting at this inclination is depending only on the depth, and will be the same in the horizontal direction in the SU plane, and also in the vertical direction, in what we call in the TV plane. So in these 4 dimensions, they are not decoupled, because for a given 3D point, the inclination in the SU plane of the image of the point will be the same inclination in the T and V plane. And since they all are all represented by straight lines that go through the origin on the frequency plane, it means we can have these expression. It means the omega S under omega U is over omega U is equal to omega T over omega V. It means they will have the same inclination in the SU and TV plane. And these things is what we call an hypercone, which is particular. It means, although the light field is 4-dimensional, it's an image of a 3-dimensional object, of 3-dimensional scene. So it doesn't have the 4 degrees of freedom, but has only 3 degrees of freedom. It means the image of a scene is, as we'd say, is a manifold in 3-dimensional, which is embedded in my 4D space. and we can do interesting things with that. Because we have this property. And so let's see. Here I made an animation which I represent. We have is a 3D X, like 3 dimensions, U, V, and S. And the third dimension, the fourth dimension, T, is time. And so we are representing is as it would be the hypercone. It's varying time because time is the fourth dimension. So the hypercone, which is the image of this point, these points at the same depth, they are like this in 4 dimensions. That's the best we can do in visualizing, or we could even visualize this as, okay, we have all V and T images, and we have an array of V and T images in U and S. You can also represent like this, and we have all these mathematics here that we have. And using the mathematics, we can actually manipulate this. For example, since we see that, like, if my point is between 2 depths, it will be in the frequency omega u, omega s in this region, and this will translate to something like that in the VT SU frequency plane. I can design 4-dimensional digital filters that can, for example, filter points in different depths. I can show you an example. This is an image, and I can, as this light field image, and here I put my focus here at the middle distance. Which is further away is out of focus, which is closer to me is out of focus, but the middle is in focus. Here, okay, I put the focus here next to me. I put the focus here further away from me. But you could say, okay, but we can do this using regular cameras, just changing my lenses. Of course, but I can do in the light field after I record this image. But using more interesting signal processing operations, we could do something that a camera cannot do. I can have an image that has which is further away from me is in focus, which is closer to me is in focus, and it's a middle distance is out of focus. Physically, I cannot do this with the camera, but using light fields, I can, doing signal processing. So, and what about light field displays? How do we represent this? How can we translate this image that I record as light field as an image in front of me without having to resort to like stereoscopic glasses with eye tracking, changing images, and so on. There are lots of devices that do so. We have this holovisual devices, for example. We have holographics, this holovisual holographic display, InnoVision, Rift Oculus, holographic displays from Microsoft. We have this Leia Ink Display, which Leia is, the name is interesting. It comes from Princess Leia from Star Wars, because in the first Star Wars movie, and the Princess Leia holograms appears in front of Luke, and so on. So they create these light field displays. We have this project Starline here that is, I can see. Here I'm recording, this is actually a display, and we can see the parallax. I'm recording the image in different parallax positions. I have the Looking Glass Factory displays. We have these interesting displays also from Avalon Graphics. I can show you a part of this video. This is a light field display because we can actually synthesize the light field in front of me, and doing so, I can see this 3D image from different perspectives. For example, here. And how it is done roughly is like this. We do the opposite that we have done using light field cameras. It means I have a display here, and actually from the different light rays that go out of this, that are focused here on my micro lens, I synthesize different rays that come into my eyes. So depending on the position that my eyes are, they will synthesize, they will see different perspectives of the object like this. And actually, we could also solve the accommodation convergence problem, because actually my light rays are coming from here as if they were coming from here. So my focus should be here. So everything is all right and everything works. So I can show some use cases for this Plenoptic function, like free viewpoint sports events when I can see a football match from different perspectives. For example, we can do this in TV, and for recording it, I could have camera arrays and so on. We can have this immersive bidirectional communication, as we have shown before. Also, we have 360 degrees video. We have this because now that we have all the light rays in space, it is easier for me to create like mixed reality things where I can put the submarine here in Paris, and I can do so in a realistic way by gracefully combining the light rays. I can do like virtual reality training using Panoptic function. We can do medical imaging. We can do remote surgery. For example, when the surgeon here is looking at like a 3D model of the heart, and it's manipulating it, and the robotic device here does the manipulations in the actual heart. See, I did not take this from a science fiction like propaganda, but actually this is something being sold. Okay, now for quite a while. We have remote surveillance with that recovery, like in using robots and cameras. We can do photography editing. We can do virtual reality surveillance with light field editing. This is interesting. Let's suppose that we have like an image taken under the sea. But under the sea, there are these particles that are suspended in the environment, and so they make the images look like this. So say they have this turbidity, and this turbidity is caused by what? By the light rays that are scattered by particles that are suspended in front of my scene that I record. But if I use a light field camera, I can like filter out using signal processing operations the light rays that are emitted by those suspended particles. And so I can do some processing and like be able to recover the image using signal processing techniques, using 4D signal processing. And so to finish, I will give just a brief notice, because this would be another talk about the standards for Plenoptic image. We have the JPEG Pleno, which is from Plenoptics, which aims at standardizing these modalities of Plenoptic representation. There is one standard already for light fields. We have standards from point clouds, from JPEG, and also from MPEG. That is one that JPEG is still discussing, but MPEG has for a long time standards for point cloud representation, and also JPEG is about to launch and standards for holography. That is a different modality of Plenoptic representation. Okay, so the standard that is already published is this one here, this 21794-2, with light field coding, published in April 2021, and by chance it had a significant Brazilian participation in its elaboration and techniques and so on. And there's also this MPEG-I, which is the initiative corresponding to JPEG Plano, but for video. And we have also studies on Plenoptic representation of video, and also using like this multiview, the processing of multiview video for recovering different perspectives and so on and so forth. And so it's all for today, and it was a pleasure talking to you, and I'll be happy to take questions if there are any.
Professor Eduardo, thank you for the very nice talk. It was a pleasure. So I'll move directly to the questions from our attendees. I also would have a couple from my own. Let's see if we have time for that. First, Sanduni asks a question. Actually, she found out the answer later on, but I would ask also to let other people know about that. What's the light field viewer used some minutes ago to show interactive refocusing?
That was a Lightroom camera.
The viewer from the Lightroom.
Yes, it actually is a software that is both inside the camera and you can have on your computer that takes the Lightroom camera images and do refocusing.
Perfect. She found out, but I think it would be of interest of others. Felipe França is asking, is light field vision like present in any kind of living beings? I think this sort of viewing style, this is somehow inspired in some animal or other sort of living beings. I think this is the question from Felipe.
Yeah, that's an interesting question. Actually, what a light field wants to do is how can I capture the richness of information, of the visual information that is in space. And the visual information in space is a combination of electromagnetic waves propagating in different directions. This is what I see, because actually my eye is like a camera that is watching, that is recording these multiple rays and focusing. But I can change focus in my eye, and I can choose the rays that I put in focus. I can move myself, I can move my eye, and I can see different perspectives of recording in my eye the light rays. Actually, but in order to allow my eye to do so, I have to capture this information, which means these multiple rays. And the trick, one of the tricks that we may use to capture this information is by recording the rays coming from different directions in the different positions in space. This is the light field. There is another trick that we say that's given by holography, because holography, instead of capturing the light rays, I capture the wavefronts of the electromagnetic energy that is in space by recording interference patterns and by illuminating those interference patterns that I record using a coherent source like laser, I can synthesize the wavefronts. And from the wavefronts, I can recover all the electromagnetic energy, because as we have learned in like physics 3 or something like that, if we have a wavefront, the wavefront is enough to synthesize all the rest of the electromagnetic wave. I don't need anything else. So it's holography. It means actually it's not, the eye actually is quite simple. It's like a camera that has a given resolution, given my sensors, and that has variable focus. But what is different is the eye, which is in space, looking at the world. The world has many different rays coming from many different directions. And when I take a 2D image, I just take like a very, very rough simplification. I take these 7 dimensions and cut to 3 of the Plenoptic function. I don't know if I was clear enough.
I hope Felipe is happy with the answer. Please, if you have more questions, please just write down. We just got another one from Sanduni. What's the algorithm used in the Lightroom software to do the interactive refocusing? Do you have those details?
Yeah, I don't have the algorithm per se, but I have the equations, which are much more fun. They are is like that. Suppose that we have
Just
a
one
light
second.
field.
Professor Hay, would you be able to present the screen from Professor Eduardo? I think he's using the slide
Yeah.
to right now.
Yeah.
Oh, much better.
See, suppose I have a light field here, X, Y, U, V, and T, 4 dimensions plus the time dimension. And suppose I have a scene that is there that is focused at the focal length f. I would take my light field and do this integral here. COX, Y, F, and T at position F is integral of my light field with the 4 dimensions plus the focal length. Using this integral, can synthesize it. But once I have my light field, my images, I can do what? I can, if I have the light field at focal plane F and alpha is F prime over F, we can synthesize another image XY focus at F prime using this integral here, where alpha is the ratio of the focal lengths. And so I think this more or less answers, and in my algorithm will just act on this light field and do this integral in sort of discrete way. And in other words, if we want to be even more visual, actually what I do, I take my U and X plane, U, the point it pierces the length, X, the point it pierces the sensor plane, and by summing for each X at a certain inclination here, I will focus at a different direction. There, I will focus at a different length. So when I vary my focal length, this inclination varies. Then my algorithm essentially it does that. For each X, it sums along the inclination that depends on the ratio of the 2 focal lengths. And I change it by summing along these different directions. Okay?
Okay, thank you. Regarding the previous question from Felipe, Caroline Conti is complementing here. She's writing that we can find a similar imaging system in nature in flies' eyes. So they are called compound eyes. So thank you, Caroline. I would like
interesting.
also.
Thank you, Caroline.
to mention that Caroline is going to speak to us during the next DPVSA, that's our school on digital processing of visual signal and applications, late October. So please find us online, DPVSA, you'll find more information. I think we don't have more questions, but I'll close with one question from my side, if you allow me, Professor.
Yes, of course.
Well, you brought many details and information regarding light fields, and we know about your contribution to light fields coding in the context of JPEG Plano. My question, however, is more like considering that JPEG Plano itself has three, it's considering three representation, right? Light fields, point clouds, and holography, like you have mentioned. My question is, how do you, this is a sort of future prediction, right? How do you foresee those sort of signal representations are going to interact in the future, or do you think they are going to have their own applications, or they are going to interact more widely in different sort of applications? My question is really towards more about the industry itself, like real world sort of applications. Do you have any comments on that?
Yeah, actually, I think my guess that it will depend a lot on how both the acquisition and display devices evolve. In terms of light fields, for example, the acquisition devices, they are like much more advanced than the display devices. They are much cheaper and much easier to use, and so on. So depending on how they evolve, we can start having like this interaction. For example, holography. Holography is very promising also, but is still much less advanced. We have some niche application like microscopy and so on. And it will depend. We have already some works that they have point clouds that are also light fields. It means for each point in space XYZ, we also record the different rays that emanate from it. It will be a light field and a point cloud. But whether it will be useful or not, it will depend a lot on the acquisition and display devices. But actually, once this becomes cheaper and easier to use, the type of processing that we can do having this Plenoptic function information, no matter how it is presented, it will give us a lot of power in terms of processing. But of course, there is the challenge because we have many light rays for a given scene, so we have a lot of information to store or transmit. It puts a lot of pressure, and so it's not trivial to process light fields in a more like advanced way, because it's hard. It's a lot of information. It takes a long time, requires a lot of computing power, and I can say the same about point clouds and holography. So the future, it will depend a lot on how those technologies of acquisition, display, and processing evolve.
So many challenges.
Yeah, and it is a fascinating subject, as Caroline may confirm, that has been working with light fields for a very long time also.
You mentioned this in a given point of your answer. You mentioned that no matter how this is going to be displayed, this is connects to another question that will be the challenge related to quality assessment, because at the end of the day you have this acquisition, you may have coding, but how do you measure the quality of your visual signal if you don't really know how it's going to be displayed, or and so there are many variables here, so there are many challenges, right?
Yes, this is an interesting question, because there is one point. if you are watching your TV, you can make quality evaluation using a 2D TV, because it's a 2D image. You see, you can make some mathematical operations in order to give a number that will be more or less correlated with the quality of the image I'm seeing. And this already happens a lot in 2D images. The problem with this information, not 3D information, but this information that is the visual information that is in space, the quality will also depend on how I interact with that. Because I'm not fixed, I'm moving, I'm changing focus, I'm doing lots of things. And how do I interact? Okay, to affect my quality. And also the quality may be affected by how tired do I get when I do this interaction. So I could also take this into account. How tired do I get? Do I get sick? Do I get headache? Or if I'm doing a remote surgery and I want to look at the heart from different perspectives, how easy is for me to interact with that? Will I get very tired? Will it be easy? Will I get irritated, annoyed? It depends. So the number of variables that I have to evaluate increases a lot. And it's interesting because in JPEG now, we are starting an activity that we would like to call for proposals of light field quality assessment systems.
Okay.
And that is, but this is quite a challenge, because the amount, the number of variables grows a lot, and it gets much more complicated. But
my question is
also fascinating.
Was really in the sense of motivating about the number of questions that are still open in this subject, right?
Yeah.
I would like to, I promise this is going to be the last question, but I must bring the question from Professor Suzin. That's he's asking if this front lens with so many micro lenses behind will be distorted by diffraction of light. Is there any challenge or problem related to this?
Yes, that is, yes. It is, because if we look at it, when I let me put here, I will arrive there soon. When, let's see this.
Professor Hayes, I think we are going to need your help once again to show the slides.
To show my slide. Yeah. See this image that is also I took from Caroline here. And it depends. The diffraction of the rays is very important, but what will be the main limitation? It means the more diffraction I have here, the worse will be here. Like I will have less. I will be able, less rays will be like reliable. It means the amount of like angular resolution that I have, or my field of view in terms of angular resolution, will depend also on the quality of this lens, on how many diffraction I have, and my resolution will depend on the number of lenses here, the quantity of lenses. The more lenses I have, the more resolution, spatial resolution I have. But if I make them too small, I will start bumping into a lot of different problems regarding the optics and so on. So this is quite challenging. And that is why, in terms of light fields, we don't have simultaneously yet at the market something that may give high resolution in terms of spatial resolution of each image, and also high resolution in terms of the number of positions that I record, or the number of rays. I cannot have both at the same time yet, due to two factors. One is the density of the sensors, And the other one is also the quality of the optics. And this is also very important and also quite critical for its success.
Okay, thank you. So this, as I promised, this is the last one. So once again, Professor Eduardo, thank you for the very interesting talk and for the nice discussion. I believe that if we had time, we would be discussing this during the afternoon, but we have time restrictions. So
Yes,
thank you.
Yes, thank you. It was my pleasure. Thank you very, very much for this opportunity.
The pleasure was ours, and now I give the word once again, Professor Hayes, to make the final comments. Thank you, Professor Eduardo, and thank you, Professor Hayes, for having me here chairing the session.
So first of all, thanks to Bruno to sharing this session today. Also thank Eduardo for this very nice, interesting talk. Thank you. Bye-bye.
Okay, thank you.